So a buddy of mine's been working on a really interesting project where he's able to identify and track phones based on the infrared transmission of the IR proximity sensor in the phone. And he's actually presenting this at the DEF CON Hacker Conference a little later this week. But when he first started doing this, he had some technical issues with actually capturing that IR signal. Now, the first thing you might turn to if you're trying to capture some infrared data is one of these little IR receivers. And these are really easy to use, little 3-pin devices. You hook up power and ground and they output IR data. The problem is that these are typically designed to capture modulated IR data. So the data is typically modulated in the 36 to 38 kilohertz range, such as if you're using a remote control for your TV or something like that. Now, if you look at the IR data coming out of the phone's proximity sensor, though, this is more in the range of 1 kilohertz, or even could be much less than that, depending on the phone that you're using. So these little guys have a bandpass filter in them that only allow the expected modulated frequency through. So they're pretty much worthless for trying to capture this kind of data. Now, of course, you could just use a photodiode to capture the IR signal, and that's exactly what he was doing. But the problem is that without amplification, the signal out of these things is really pretty weak, and he couldn't reliably capture data from any phone unless it was, an inch or two away, which really wasn't very practical if you're trying to, track someone or identify a phone at a distance. So I put together this little circuit, which is really nothing more than a photodiode amplifier and a comparator, but it increased his range from, 1 or 2 inches to 15, 20 feet or more, and made it a lot more practical for what he was trying to do. Now, the circuit is not very complicated, but there are some very interesting caveats and design decisions you have to consider when you're building a photodiode amplifier. So let's go to the whiteboard and take a look at the circuit. So your typical photodiode amplifier consists, of course, of a photodiode and a transimpedance amplifier, which takes an input current and outputs a voltage. Now, what happens when photons strike the PN junction of a photodiode is it will actually emit charge carriers. So the output of this sensor is fundamentally a current. Now, that current is going to interact with the high input impedance of the op-amp and start to develop a negative voltage here. Now, since this is a inverting configuration, that negative voltage is going to cause the op-amp to want to output a positive voltage. And since the op-amp's non-inverting input is tied to ground here, it's going to want to output a voltage such that the current it feeds back to its inverting input counteracts the current from the photodiode, keeping this node at 0 volts. Since, of course, an op-amp always wants to keep its two inputs equal. And so the output voltage we get from this circuit is simply the current multiplied by the feedback resistor value. That's just Ohm's law. Voltage equals current times resistance. And so by increasing the value of this feedback resistor, we can amplify the current signal from the photodiode, and we get a voltage output from this circuit. And of course, as the intensity of the light hitting the photodiode increases, that will increase its current, and we'll get a larger output voltage here. So ideally, our output voltage is going to be linear with respect to the intensity of the light striking the photodiode. Now, while this is a very simple circuit, there is one major problem that you'll run into a lot of times with this particular configuration, and that is unwanted high-frequency oscillation. Now, the reason for that is because, like any PN junction, there's some inherent capacitance in this photodiode. So in effect, what we've done is we've hung a capacitor right off the inverting input of the op-amp. Now, when the op-amp's output signal traverses through this resistor and interacts with this capacitor, there's going to be some phase shift there, just like you have with any low-pass filter, which is effectively what this forms here. And at some frequency, that phase shift is going to be 180 degrees. Now, of course, the op-amp, since it's an inverting configuration, has already flipped the signal by 180 degrees. So if this feedback network flips it by another 180 degrees, we have positive feedback. And so if your gain at that particular frequency where you get that positive feedback is 1 or more, then you have some really good conditions for oscillation here. And that's almost always unwanted in this type of circuit. So In order to counteract that, we need to add a capacitor in the feedback path. And what this capacitor is effectively doing is providing a short circuit around this feedback resistor at higher frequencies, since higher frequencies are going to see a capacitor as a lower impedance path. In other words, what we're doing is reducing our gain at higher frequencies. And that way, at that frequency where we have a full loop gain of effectively 0 degrees, we have positive feedback, we've reduced the gain so much that we don't have a gain of 1 or more, and therefore we prevent oscillation. Now in this particular application, because the signals that I'm trying to detect are fairly weak, I wanted a whole lot of gain, so I put in a 10 mega ohm resistor here as my feedback resistor. Now with this large of a resistor, really any stray capacitance on the PCB in parallel with this, even 1 or 2 picofarads, is probably going to be enough to prevent oscillation, but just to be sure, I threw in a small 2.2 puff capacitor across that feedback resistor in the circuit. Now, one of my concerns with this circuit was keeping the op-amp from saturating. This design was intended to run off of a 3-volt battery, so I really don't have a whole lot of voltage headroom to work with here. And even with rail-to-rail op-amps, their output cannot go all the way to the positive or negative rails. So with no current coming out of the photodiode, let's say there's absolutely no light striking it, this point is going to be 0 volts. And so the op-amp's output's also going to be 0 volts, or it's going to try to output 0 volts. Most rail-to-rail op-amps, some can, but a lot of them can't go all the way down to 0 volts. So you're actually going to end up saturating the op-amp's output. Now, in some cases you can get away with that, but op-amp saturation recovery is not a well-defined or guaranteed parameter by manufacturers, so it's really best practice to prevent the op-amp from saturating. So in order to do that, I just added some bias resistors, just to keep the reference voltage on the positive input of the op-amp at just under 200 millivolts here. And so that prevents the op-amp from ever going down to 0 volts, and with most rail-to-rail op-amps, a couple hundred millivolts is sufficient to keep it from going into saturation. Now the reason why I chose such a small voltage here instead of maybe biasing this at half rail is you do have to be kind of careful about biasing your photodiode. Now in my situation, I wanted to get as much sensitivity as possible, and if you reverse bias a photodiode, you're actually going to get less sensitivity. So the more you reverse bias it, the less sensitive it's going to be. Now there are some other advantages in some cases of reverse biasing the photodiode, but you do lose sensitivity, and I didn't want to do that. So I wanted to keep the quiescent bias across this fairly low. So 1 to 200 millivolts is going to be small enough that it's not really going to make a noticeable effect here. Now on the other side of the coin, because I have so much gain here, I have to worry about the op-amp's output slamming into the 3-volt rail. So yeah, it's great to have lots and lots of gain when you're trying to pick up weak signals, but as soon as there's a strong signal that comes along, this op-amp's output is just going to slam right up into the 3-volt rail, and again, it's going to saturate. So to prevent that, I put in a couple of diodes. Or more specifically, I put in 3 JFETs configured as diodes. Now, I chose 3 because the voltage drop across each of these is going to be, about 0.7 volts. So that means that when the op-amp's output gets to be a little over 2 volts, these are going to turn on and short circuit the output to the input, and it's going to clamp the op-amp's output at just over 2 volts. And although nominally I'm going to be running this op-amp off of 3 volts, it is battery operated, so that voltage is going to drop, and I wanted it to operate down to 2.5 volts. So even at the lowest voltage rail of 2.5 volts, that's going to prevent the op-amp from saturating. Now the reason I chose to use JFETs as diodes instead of a typical silicon diode is they tend to have a lot lower leakage current. So the reverse leakage going through these is going to be a lot smaller typically than a normal silicon diode. So we're going to leak less of our signal through this path, and generally leaking your signal through an unwanted path is undesirable. So I went with JFETs here instead of a typical silicon diode. Now another thing to consider is noise. Now obviously you're going to have noise generated from your feedback resistor and noise generated from your op-amp and everything else, but a proper noise analysis of a photodiode amplifier is actually fairly involved. Although the basic photodiode circuit is really simple, the noise analysis is not so simple. And there are books written on the subject. Highly recommend you read them if you're interested in that. But to be honest, in my experience, the biggest source of noise is not the internally generated noise, but externally generated noise. And there's generally two ways that noise is going to get into this circuit. One is through electromagnetic pickup. So you've got this feedback path here. You're basically creating a little loop. And so if you don't keep this physical layout nice and tight, you kind of let your traces wander all over and you do a sloppy layout, you're basically building a pickup loop here, and you can pick up electromagnetic interference there in your feedback loop. So you want to make sure in your physical layout you keep this as tight as possible. The other and probably most obvious source of unwanted noise is going to be light striking the photodiode. Right? I'm only interested in infrared signals from phones, but there's going to be all kinds of other sources of light striking the photodiode, and that's unwanted noise. And the best way to deal with that is to try and prevent that unwanted light from hitting the photodiode in the first place. And the two basic ways to accomplish that, you can put a physical shroud around the photodiode, and that just prevents any ambient light from directly striking the photodiode. And of course, you can also put in filters. So you can put in a filter to only pass IR signals and block out anything else. Although, like with any bandpass filter, it's not going to be perfect. There will be light that's going to get through. And some unwanted sources may actually be other infrared signals. So, it's not a perfect solution. However, beyond the physical filtering of the photodiode, there are some things we can do to try and mitigate some of these problems caused by unwanted light hitting our sensor. So first of all, consider what happens if you walk into a room with overhead lights. Well, you're going to have some ambient light that hits this photodiode, no matter how well you shield it and filter it. And so that's going to cause the output of the op-amp to have some DC offset. So let's say that after this photodiode, we're going to be looking for pulses of IR light. And since this is really just on-off pulses, it's very easy to just feed this into a comparator and say, well, all right, anything over, 50 millivolts, we'll consider a high state, and anything below that we'll consider a low state. So we put our threshold at 50 millivolts, and all's well and good. However, when we're in a room that has ambient light, and that produces a DC offset, we could have problems here. So you can clearly see with this DC offset in the signal, we're always going to be above this 50 millivolt threshold that we picked. And so we're never going to see a high to low transition. Even though looking at the signal, we can clearly still pick out that desired IR signal, our threshold that we chose is too low. So to counteract this, the easiest thing is to just knock out that DC component. So that's easily done with a DC blocking capacitor. Now I also added a terminating resistor here to form a high pass filter, and that just helps knock out any 60 hertz or 120 hertz pickup you might get from overhead lighting or what have you. So you can see the output from the photodiode amplifier picks up the IR signal from my phone pretty much as soon as I pull it out of my pocket there. But this is still an analog signal, so we have some varying voltage levels, there's a little bit of noise in there, and you can see due to that DC blocking capacitor that on the falling edge of those IR pulses, we get a bit of a negative going voltage here. But we can clean all that up and digitize it pretty simply with a comparator. Now the comparator circuit is fairly straightforward. These two resistors set the threshold voltage for the comparator, while these two provide a little bit of hysteresis. The only thing out of the ordinary is this Schottky diode, which I just added in order to protect the comparator's input from those negative voltage spikes we saw on the scope. So if this voltage drops below about negative 200 millivolts, that will turn on this Schottky diode and it'll clamp that voltage there and provide some input protection to the comparator. And as you can see, that comparator works just as expected. We get some nice clean digital pulses here whenever the photodiode detects the output from the phone's IR proximity sensor. Now, as for individual component selection, none of the resistor values are really critical. They don't have to be that precise. I just use 1% resistors throughout. The bypass capacitors are all ceramic X7R type, and the capacitor in the feedback path of the amplifier is a higher quality NPO type. Now the photodiode I selected based on sensitivity, since that was my primary concern. This particular one has a fairly large reverse light current specification, which means it's pretty sensitive. In fact, it was the most sensitive out of all the photodiodes that I tested. As for the op amp, because this is operating as a transimpedance amplifier, generally for any transimpedance amplifier, you want it to have a really high input impedance. So you want very low input bias current here. Of course, the reason for that is your input signal is a current. So any current that is going into the op amp is basically lost. You're losing that part of the signal. So you typically want to choose a op amp with a high impedance FET input, preferably one with low current and voltage noise as well. In my particular application, because this is going to be a battery-powered device, I also wanted it to be a rail-to-rail op amp that was capable of operating off of 2.5 to 3 volts and which had low current consumption. So this TSV911 from STMicroelectronics fit the bill quite nicely and is really cheap, even in single quantities at only like 70 cents off of DigiKey. So really nice little op amp. It also comes in a SOT23 package, which is really nice because I had some space limitations in this design as well, which we'll look at when we take a closer look at the circuit board. Now, as we discussed, the JFETs are used here as diodes because of their low reverse leakage current. And the 4117 is particularly good in this regard. It can have leakage currents down even below 1 picoamp. So obviously that's important because, we don't want to pick a nice op amp here with low input leakage and then slap in some really leaky diodes here. So the 4117 is a really nice choice when you need low leakage diodes. And finally, the comparator selection wasn't really critical besides space and power consumption requirements. The TLV3201 from Texas Instruments fit the bill quite nicely and comes in a nice little SOT23 package just like the op amp. So that was quite a nice fit for this project. Now the physical dimensions of the circuit board itself were chosen so that it would fit inside the lens cover of a rifle scope that we had. And you just have the photodiode centered there in the middle of the board. And it's just big enough to fit a CR2032 battery on the back, which provides power to the board. And finally, the circuit's quiescent current consumption is less than 800 microamps running off of a 3-volt supply. And that gives a pretty reasonable battery life when powered off of that CR2032 battery. So this was a really fun little project. I got to learn quite a bit about photodiode amplifiers, and hopefully you did too. And if you happen to be in Vegas this week, be sure to stop by the Wireless Village at DEF CON and check out my buddy's talk on how he uses this IR data to identify and track phones. Thanks for watching, and as always, please leave any questions, suggestions, or corrections in the comment section below.